This is Brian from Class 2 Group 10 and I'll be presenting Task 1. Here we create a linear regression model to predict COVID-19 death rate using at most 4 features. We hypothesize that death rate can be reasonably predicted using hospitalization rate, vaccination rate, GDP per capita, and population density. We also consider the use of COVID-19 testing rate as a backup feature for the previous features in case they were not appropriate. Here we define functions that we will use later for visualization and prediction. So we use the our world in data COVID-19 dataset, and here we read the dataset into a pandas data frame. We then pre-process the data, dropping all null values, all rows with null values, and negative values. We then perform some exploratory data analysis where we plot the distribution, scatter plot, and correlation heat map of all features and targets. So this will inform our feature selection and transformations later on when we iterate and improve the models. So here we provide some evaluation and justifications as to why we perform the transformations that we did later on. Here we define the metric used for our model evaluation, which is root mean squared error, and we argue why this is preferable over other metrics. We then say that a reasonable prediction is a root mean squared error of 1 or less. Here we perform the predictions and subsequently iterated over the original prediction by performing some feature selection and transformation techniques. And eventually, we managed to decrease the root mean squared error. So we made the assertion that it is difficult to predict death rate using the features that we have selected. And then we compared our Python model with Excel and concluded that they both agree with each other and give the same error scores. We then concluded that predicting COVID-19 death rate may not be very possible using linear regression, and that other nonlinear models may be more appropriate for this task.
For task 2, we aim to predict the ICU occupancy per day. The widespread of COVID-19 has imposed huge stress to healthcare resources and overwhelmed the healthcare systems. Sometimes seriously ill people cannot get immediate treatment since the beds in ICU are limited. Under this situation, it is helpful if we can roughly predict the number of patients will be sent to ICU so that the resources can be allocated more appropriately for treatment of these patients. We selected the following data as our features: new cases mode per million, stringency index, population, and human development index. In order for early preparation, the data used for new cases mode per million and the stringency index is 7 days before to predict the number of ICU patients in a given day. These two values reflect how serious the situation is, so we expect to see more ICU patients if these two values are high. Population and human development index are used to represent each country, since situation might be different for different countries. The dataset we use are our world in data COVID-19 dataset and our world in data number of COVID-19 patients in ICU per million. We extract the columns we will use from the datasets and check whether there's any missing value in the datasets. After that, we did some data pre-processing. 3 main tasks are done in this part, including drop rows that contain missing values, drop rows that contain negative values for new cases mode per million, or daily ICU occupancy per million, which make no sense, and merge the two datasets based on the location and the date. Before we merging the two datasets, there is a shift to the date in the first data frame to 7 days later, given that we will use the previous information to predict current situation. Then we extract the features and targets from the merged dataset. After that, we did some exploratory data analysis to see how the features distribute and how they affect our target. Read from the correlation heat map. New cases most per million show the highest positive correlation with the target. Stringency index shows a moderate positive correlation. Population is a weaker predictor compared to the first two features. And human development index almost has no correlation with our target, given the correlation coefficient is extremely low. Before feeding this data to our linear regression model, we need to mention that the metrics we use to evaluate the model is a root mean square error, since it can penalize large values and is also the same unit as the target. We use a function, process and display LR, for perform the regression and display the required statistics and results. The coefficients shown in the right graph here agrees with our correlation heat map. New cases smooth per million is the best predictor. Stringency index is also related but less important. And the explaining ability of population and human development index is pretty weak. We also try to improve the accuracy of the model by transforming the feature new cases smooth per million by using square root. And the performance indeed improves by doing so, which is shown by increased R-square value and a decreased root mean square error. After obtaining the coefficient of the model, we predict the target of testing dataset and plot the first 20 actual values against predict values for comparison. And here's the result. Some further improvements of the model can be adding some more related features, such as demographic information of daily new cases, since older people are more vulnerable to COVID. And more features should be used to describe a country instead of only using population and human development index. Policies and healthcare equipment may be more useful to represent the situation in different countries, but they are also harder to quantify. Only if there is a way to quantify this information can we adopt them into our model. In conclusion, by knowing the new cases and stringency index 7 days before can roughly predict the number of ICU cases. So it's crucial for a hospital to get these data to have early preparation. However, population and human development index are not good predictors, and more features should be added if we want higher accuracy, but only after they are available.
I will now explain our web page. We can add or remove any number of features that we would like, and we can define for ourselves the value of each feature and as well as the name. And it will give its corresponding prediction. Now we will switch over to ICU prediction, which is the target for our task 2. And you can see that all the buttons that are not needed are disabled, and that the fields are automatically populated for you. So now let's enter some real-world values for Singapore. In this case, we will assume that Singapore has about 2,000 new cases every day. And you can see that it gives this prediction, and it also performs the normalization for us, so we do not have to worry about normalizing when we enter the X values. So that's it for our web page. Thank you.